My name's Jenna McGovern. I'm a PhD student at the SMI. This project actually came about as sort of an offshoot to my PhD that I really had burning questions about, wasn't really going to fit within the scope. So I basically decided to head up this project with one of my supervisors, Karen Connors, but also I'm supervised by Steve and Greg Webb, who's over on main campus of UQ. So yeah, basically this project was born out of my PhD, which focuses on understanding how we can better point towards lead zinc mineralization in northwestern Australia. And I have realized when looking back at these slides after the deadline passed that one of my figures didn't pop across. So if you imagine in your mind's eye that there's a picture of Australia halfway between the Pilbara and the Kimberley, very well-known regions, there is a giant gap in most of our geological pictures of Australia, minus groundwater. We understand the groundwater in the Canning Basin very well, but going back about half a century now, it was a hub for lead zinc mineralization exploration. And one of Australia's largest deposits is still in this area and remains unmined because it's over a kilometre down underground. So the reason why this is a giant black hole of Australia's data on the geology is because of the depth of cover in the region, and therefore it hasn't really been able to be examined in great detail because a lot of stuff was either mined out before we had the techniques down pat to look at the geochemistry of the area, or is still too deep and behind lock and key of a mining company who I'm sure are sitting on something that will be mineable at some point because, spoiler alert, low temperature carbonate hosted lead zinc mineralization is also prospective for a suite of critical minerals. So gallium, germanium and indium globally are understood to exist within this deposit type, frequently lumped in with MVTs, but more broadly are just formed at low temperatures. So we're talking between 100 to about 300 degrees and hosted in carbonate strata. The objective of this project was just to fill in a bit of that gap by looking at a deposit that has remained uncharacterized up until now. Was mined out back in, I think, the 80s, but luckily, because geologists also like to hoard things, there is someone down in Melbourne who was able to donate a section of the ore from this deposit that was sitting in a room desperately waiting for somebody to look at it. So thank you to Malcolm Wallace from the University of Melbourne for that. The really exciting findings were twofold. One, this deposit did show that there was gallium and indium levels that were above what you would usually expect overall in sphalerite, with gallium being towards the high end of what you would expect in these enriched zones of sphalerite. Germanium actually being incredibly low compared to what we would expect, which does open up a lot of questions around the formation of this deposit and whether or not we understand how these metals move together or separately. And that has ramifications for then how we model these mineral systems to find more of them in the future. And indium popped up at about mid-range to what we would expect, but again, this is an area where this is elevated compared to kind of your average in the crust. And just the other interesting thing to note is that when we looked at how these elements were distributed within sphalerite, the zinc ore mineral that we're concentrating on in this deposit, something like iron forms quite consistently just as the crystal forms. You can follow it along the crystal boundaries, basically enriching and depleting as that comes out of the fluid. However, when you get into the metals that these minerals are known for, the distribution changes, and you can see that lead and silver follow similar traits, and then gallium and germanium are completely different. So this is where you're seeing a lot of the ore minerals move together, except for germanium, which has been the interesting finding out of this that we didn't expect. So yes, just a few findings, but I think I'm out of time, so thank you.